Hi, we'll talk about chain-based signatures. So the scenario is we have some one-time signature scheme for arbitrary length messages. So for example, we could use Lambert's signature scheme. And now we want to create a signature scheme that's multi-time secure. So the adversary can query as many messages as he wants. He will get signatures for this. And our initial trade-off for this is that the signature scheme will be stateful, meaning that between invocation of the sign algorithm, the sign algorithm keeps some state. So the idea of chain-based signatures is pretty simple. We start with some public key, pk1, and that's our public key. And now the idea is that whenever I sign a message, I already generate the public key that I'm going to use for the next message. So let's say I'm signing message M1. This is my first message. What I'm doing is I'm generating a public key pk2, so a public key for the next invocation, but I'm not using it yet. And now I'm signing this with a signature. So sigma prime is a simple one-time signature of this message, so the M1 and the public key I'm going to use next, under the secret key sk1. So and then this is my signature on M1. Now let's say I want to sign another message M2. I'm doing the same thing. I'm generating the public key for the message for my M3 when this will come about. And now I'm signing this tuple with my one-time signature again. This time I'm using sk2. And so on. So in every step, essentially, I am generating the public key secret key pair for the next signing invocation. And then I'm just signing the public key for that to essentially get this chain. And then the signature for M2 will be this whole thing. And if I want to check the signature, I would have to check that this one is a secure signature under PK on this message. And then that this one is a secure signature under this PK for this message. And then this can be extended arbitrarily. So if I wanted to sign message M3, the same thing happens. And then the signature will again be this whole thing. And in addition to the checks I already did for M2, I now also have to check sigma 3 prime, and so on. And the intuition for security is that the adversary will see these chains. And now what he could try is try to choose any of these public keys and try to make a forgery for those. So essentially he could interrupt the chain of signatures here. So just ignore all of the rest that's already there. And he could then try to forge a signature, for example, under pk3 on a message m3 prime. But of course, our signature scheme that we're using is one-time secure. And essentially, we've only used this pk3 once, namely to sign this thing here. The adversary should not be able to generate a signature on this different message. And the formal security proof is actually also not that difficult, so let's just do it. We of course do this by reduction, by constructing an adversary against the one-time signature scheme. So as usual, we start with an adversary against the scheme that we want to prove secure, and we construct an adversary against the underlying scheme, which is the one-time signature scheme pi prime. So what's happening in this? Well, A prime is an adversary against the one-time signature scheme. So from his challenger, he gets some pk star, which is the public key that the challenger chooses in the one-time signature game. And A prime is allowed to ask one query. So what you need to notice is that we get only one public key, pk prime, and our forgery needs to be with respect to that pk prime. But as we talked about in the intuition, essentially the adversary can always take any part of this chain and try to come up with a different signature for the public key that's in this position at the chain. So what we need to do is somehow embed our public key pk star into all this. Do you have a good idea how to do this? Exactly. So we do index guessing. We need to guess at which point the adversary will do this interruption of the chain and for what public key he's going to give us the forgery. So let's do a little bit of index guessing. Where as usual, Q of n is a polynomial upper bound on the number of signatures that A may query for. Because A is a PPT, Q of n is just polynomial. So we choose a random index between 1 and some polynomial upper bound. And the idea is that we will embed our public key pk star at that position. And all of the other public keys we will just generate honestly so that we also have the secret keys for them. So now we have the following situation. We have a bunch of public keys where we know the secret key for, and we have exactly one public key where we don't know the secret key, but we're allowed to ask for one signature. Now A expects to get the public key for his whole scheme, which is just the first public key. And now A will ask for signatures. So when A asks for a signature on mi hat, essentially we will need to generate such a tuple. The interesting part will be the signature here. And for this, there are two cases. Either the signature should be under public key where we know the secret key. Then obviously we can just generate the signature and everything will look fine. And the other case is where we don't have the secret key that we would need to generate the signature. In this case, a prime would just ask its challenger for this one signature that it's allowed to ask for. And this happens exactly if I is equal to I star. So for the I star query, we would have to use pk I star, where we don't have the secret key, so there we ask our challenger. And all the others we can just generate honestly, because we have the secret keys. So eventually A will output a candidate forgery. And this candidate forgery will be like a whole chain of signatures, because the signature in the scheme that A is attacking needs to be like a chain of signatures that begins at pk. So syntactically, the signatures that he's giving us need to look like a chain, like up here. Now, well, the only thing that we can hope for is that actually this whole chain of signatures at some point contains a forgery for our pk star. So let's hope for this, and if this works, then we just output this forgery. So let's talk about why this makes sense. First of all, you need to notice that these public keys that A uses in its chain, they're not necessarily all the same that we've used in our chains when answering the queries. Because it may happen that A may have forged a particular signature and just replaced the public key that was used there with one of its own. Obviously, this shouldn't happen because he shouldn't be able to forge signatures, but for the sake of this proof right now, we don't have any guarantees about this. However, A is not completely free in replacing all of the public keys, because there's one public key that A cannot replace, and this is pk1. Essentially, this is why in the verify algorithm, this part here is very important, because it says that in the chain that A outputs, the first public key is actually the public key that we gave it. So the chain definitely begins at pk1, and then it may also go on with pk2 and pk3. At some point it may diverge. So if we look at all of the messages that we got signatures from A, they are the following. And now we're looking for the first message that's different from the one that we created during the experiment. So let's say this first one here, that's still the same as we had. And maybe the second one is too. But at some point there needs to be one message that's signed with the one-time signature scheme that's different from the one that we used during the experiment. Why is this? Right, because A is claiming a forgery. If he wants to win his signature game, then ML so the message that this whole chain is a signature for, must not be one of the messages that he's queried. So this is a completely new signature. So at the very latest, this last tuple is definitely not the same as the one that we used. Because clearly ML cannot be ML head. So at some point in this chain, there needs to be the first index where it's not the same as in our chain. So let's say the first two are equal to the chain that we had, and then the third one is the first part of this chain that is not the same as in our chain. Then this is our forgery. So because this chain validates correctly, the signature sigma 3 prime is a valid signature on this message under this public key pk3 prime. And we know that up until this point, the whole chain was still the same that we had in our experiment running with a prime. So in particular, this pk3 prime here, it's the same as pk3. So it's the same as our public key in our chain. So let's talk about what happens if we were lucky. Let's say by chance we actually guessed the index I star to be 3. Then what happened in our run of the experiment? So if I star is equal to 3, then this pk3 here, the important key, this is actually our pk star that we've embedded in that position. And when we did the experiment, the one signature that we asked for was a signature on this message. And we had pk4. And now we know that this message that we asked for is not the same message as the adversary output, because this is how we chose this position in the chain. It's the first one where this message deviates. And so if we output sigma 3 prime as a forgery on this message m3 pk4 prime, then this is a valid forgery, because it's a valid signature under pk star on a message that's different from the one that we have queried a signature for during the experiment. So overall, if we're lucky and our I star happens to be equal to this position in the chain where the first deviation happens, then the signature that we output is exactly the forgery. So now you can do the whole probability analysis, but it's kind of boring because we do this essentially every week. The thing is, you can boil this down to the statement: we have this first index where this chain deviates from our chain, and this needs to exist. We guess I star with probability 1 over q of n. This is exactly this first deviating index. Notice that A doesn't know which I star we chose. For him, everything looks the same. So the chain that A outputs is independent of our I star. So with probability 1 over q of n, we guess this first deviating index correctly. And if that happens, we win. So just for completeness sake, so if we look at the probability that our A prime wins against its one-time signature game, that happens in potentially more cases, but one case where this happens is if A outputs a valid forgery. So valid in the sense of the signature scheme that it is playing against, meaning that all of this is valid and ML is not one of the messages that he has queried before. And we have guessed correctly. So like this I star was guessed correctly, meaning it's the first deviating index in this chain where this deviating index always has to exist. And then we can split this up into the probability that A wins and the probability that we guess correctly, assuming A wins. This split up is mostly because the event guess is only kind of well defined if the adversary A actually wins, because otherwise this deviating index does not exist. But we know that if A wins, this deviating index exists, and because everything is independent, we guess it correctly with probability 1 over Q of n, and then we're just stuck with the probability that A prime wins is at least the probability that A wins divided by Q of n. In the end, we know that this probability that A prime wins is negligible because it plays against a secure one-time signature scheme. And then because Q of n is only a polynomial, we can deduce that the probability that A wins also needs to be negligible, which is what we wanted to show. So that's it for chain-based signatures. The scheme is very simple, and the proof also is very simple as soon as you know this trick, looking for the first deviating index and being able to argue that this index actually exists. So thank you for your attention, and see you.